Hello, in this particular video we are going to see about one of the important name reactions, that is the Birch reduction reaction. In Birch reduction reaction, what we do is that we try to reduce some of the difficult to reduce substrates such as benzene ring. Conjugated double bonds can be reduced using Birch reduction reaction, and also Birch reduction reaction can be used to reduce non-terminal alkanes, and there are several other applications of Birch reduction reaction which we are going to look into in this video. Okay, so in Birch reduction reaction, what is the reagent that we use? The reagent that is used in Birch reduction reaction is sodium metal dissolved in liquid ammonia. So this is the reagent that is used in Birch reduction reaction. Now there is a lot of significance for this reagent. The reagent contains a metal. Now the sodium, usually it is not necessary that sodium metal is always used in Birch reduction reaction. For that matter, any alkali metal can be used in Birch reduction reaction. The most commonly used alkali metals are, one is lithium, the other one is sodium, the other one is potassium. So lithium, sodium and potassium are the three alkali metals which are used in Birch reduction reaction. Now there are some other metals as well which can be used, such as calcium, then magnesium, zinc. They can also be used in this reaction. Now the importance of the metal here is that we all know that metals are electropositive in nature. So the metal that is present over here will readily, so I'll represent it as M. Okay, so the metal will readily lose its electron and get converted into M++ electron. So the electron that is generated here, okay, the electron that is generated over here, this electron is used for reduction. So reduction means gain of electrons, right? So the metal is providing the electron that is required for the reduction reaction. That is why we are choosing an electropositive substrate, that is electropositive reagent, that is alkali metal. Now what is the role of this liquid ammonia? See, when you dissolve sodium metal in liquid ammonia or any metal in liquid ammonia, the solution turns deep blue in color. The solution basically turns deep blue in color. The reason for this is because the electron gets ammoniated. The electron that is released from here gets ammoniated because of the presence of ammonia. Ammoniated means the electron will be surrounded by ammonia, like ENH3. X moles. Okay, so how many moles you are taking, those many moles will be surrounded, and this will form a complex. This complex has a blue color. Okay, that is why the solution looks blue in color, and this ammoniated electron is used for reduction of the substrate. So in this reaction, in Birch reduction reaction, so the reagent is sodium in liquid ammonia, and since it is supplying an electron, it is going to reduce the substrate, right? So the reagent's HOMO, that is a highest occupied molecular orbital, reagent will serve as your HOMO, and the substrate is going to gain the electron from the reagent, right? The substrate is going to gain the electron from the reagent, so the substrate will act as the LUMO. So the interaction here is between the HOMO of the reagent and the LUMO of the substrate. And one more important aspect that we have to note over here is that the substrate whichever we take, okay, if the substrate has any electron withdrawing group attached, if it is attached with the substrate, then what will happen is that the rate of the reaction will increase. The rate of Birch reduction will increase. The reason is quite obvious, because here Birch reduction increases. The reason is because in Birch reduction the substrate's LUMO is getting involved in the reaction. So if you have to increase the rate of the reaction, obviously electron withdrawing group will decrease the energy, right? Electron withdrawing group, whenever they are attached with your substrate, they are going to decrease the energy. So if the energy is decreased, then obviously it is going to act as a better LUMO and it will interact in a more efficient way. Now let's look into the applications of Birch reduction reaction. So there are certain applications that in which we can use this reagent. Now the advantage of using this reagent is that this reagent directly provides or supplies an electron to a substrate. So since it is directly providing an electron to the substrate, it is very easy, okay, to reduce substrates. So some of the important applications of this reagents are, the first application being reduction of conjugated dienes. Reduction of conjugated dienes. So whenever we have two double bonds on alternate carbons, we call them as conjugated dienes. Dienes basically means two double bonds attached to a single substrate. If you have two double bonds which are alternate to each other, we call conjugated. Basically, we have three types of dienes. One is called as isolated. The second one is called as cumulated. And the third one is called as conjugated. Now the difference between the three is that, say for example, if I take a substrate which contains 1, 2, 3, 4, 5, okay, 6 carbons. Now if I say it is isolated, isolated dienes means there are going to be two double bonds present, but the two double bonds are going to be present at two different positions. Okay, they are going to be present far away from each other. Then we call it as isolated dienes. In case of cumulated dienes, if I have these many carbons, if I have a double bond present here, the next carbon is going to have another double bond. So the two double bonds are present on adjacent carbon, then we call it as cumulated dienes. Now when we say conjugated dienes, it means that if there is a double bond in the between first and second carbon, the next double bond will be present between third and fourth carbon, and then the next double bond will be present between fifth and sixth carbon. So if alternate double bonds are present, we call them as conjugated dienes. Okay, so the Birch reduction reaction, or the reagent, that is sodium metal dissolved in liquid ammonia, this can reduce double bonds. But what kind of double bonds can it reduce? It can reduce only conjugated double bonds. It can neither reduce isolated double bonds nor it can reduce cumulated double bonds. It is something that you have to remember. It can reduce only conjugated double bonds. Okay, so let us see into the reaction how exactly this happens. Okay, so let me take a substrate. So let the substrate be like this. Okay, so there is going to be a double bond over here, and then in this carbon there is a double bond. So this is a conjugated system, double bond followed by a single bond followed by a double bond. Now the reagent that I am adding is sodium metal dissolved in liquid ammonia. Now what happens here exactly? So in the first step, since it is conjugated, it can participate in resonance, right? So what will happen? This double bond can shift to this carbon, and this double bond can shift over here. So if there is shifting of double bonds like this, your substrate is going to change. So here there is going to be a negative charge on the first carbon, and then the double bond has shifted over here. So this carbon is going to now get a positive charge. Okay, so there is a negative charge over here and a positive charge over here. Now what will happen is that, since you are adding sodium metal in liquid ammonia, this ammonia will donate a proton. Okay, or you will have another. Usually in Birch reduction, the proton source is ethanol. We add ethanol for providing proton. This is called as the proton source in Birch reduction reaction. Okay, so from here you are going to get H plus. Okay, so this minus charge that is present over here is going to accept this proton. So what will happen here is that in the next step, so this part is going to get neutralized. So there is going to be a double bond over here, and there is a negative charge. Sorry, there is a positive charge, and here hydrogen has been attached. Now here there is a positive charge. Now the sodium metal is going to donate its electron. It will get converted into Na plus electron. This electron will go and get attached over this positive charge. Okay. So what will happen? Only one electron is getting attached in the first step. So when one electron is getting attached, there is going to be a radical. Okay, so there is going to be a radical. In the next step, what will happen is that another sodium metal will donate another its electron. One more electron it is going to be donated, and thereby it is going to now form a anion. And in the last step again, ethanol will donate H plus ion, and this H plus ion will get added over here, and this particular double bond has been reduced. So your final product is going to look something like this. Okay, so what we have done here is that there are two double bonds, right? In conjugated diene there are two double bonds. One double bond has been reduced, the other double bond has been shifted. So this is the product of the reaction. So there are two things that you have to know. One is the sodium metal dissolved in liquid ammonia can reduce only conjugated dienes. Now how is the conjugated diene reduced? Because in conjugated diene there are two double bonds, so it can involve in conjugation, and through this mechanism two sodium metals are involved in the reaction. They supply two electrons to reduce the double bond. Okay, so this is the first application of sodium metal dissolved in liquid ammonia. Now the second application of the Birch reduction reaction is reduction of non-terminal alkynes. Okay, non-terminal alkynes can be reduced using Birch reduction reaction. So that is the second application. So our second application is reduction of non-terminal alkynes. So alkynes will be reduced to alkenes, right? So non-terminal alkynes will be reduced to trans-alkenes. That is more important. Non-terminal alkynes get reduced to trans-alkene. Now let us see how this occurs. Okay, so let me take a non-terminal means basically the triple bond is present in between. It is not present in the terminal position. Let the substrate be CH3, C triple bond C, CH3. So this is an alkyne. Okay, butane. Now what I am doing is that I am adding sodium metal dissolved in liquid ammonia. Now what will happen? Again there is a triple bond, right? So there is going to be a shift of electron. Let the electrons be shifted like this. Okay. So if the electron is going to be shifted like this, I'll draw it over here and show. So you're going to get CH3, C minus, and then there is going to be a double bond and then carbon. This carbon is going to get a positive charge and then CH3. Now since we are adding sodium in liquid ammonia, so the sodium metal is going to act as your electron source. So it will be providing electron. So this electron, what it will do, it will get attached to this particular carbon. So first only one electron is getting attached. So it's going to form a radical. So the product is going to look CH3, C, double bond C. So here there is a negative charge and here there is a radical. Okay, so the electron has been provided by sodium metal and then CH3. Now what happens is that this is your intermediate. If you can see over here, the negative charge and the anion, okay, sorry, the radical and the anion are present on adjacent carbon. So if they are present on the same plane, there is going to be repulsion. Okay, there is going to be repulsion. In order to avoid the repulsion, what happens here is that this part is going to shift. Now how will we show it? So here CH3C double bond C. Okay, so the negative charge is going to be present over here and the radical is going to be present on that side, CH3. So the radical and the negative charge have shifted to opposite positions. So the plane will bend slightly in order to avoid the repulsion. Now in the next step, what will happen is that again ethanol. Okay, ethanol is going to provide the proton. Right, from ethanol you are going to get the proton. That proton will be added to this negative charge. So this negative charge is going to get protonated, and because of protonation what will happen? CH3, C, double bond C and then CH3. Here there is going to be one hydrogen. Again similarly here, since there is only one radical, again in the next step sodium is going to provide another electron and it will convert it into a anion. And in the last step that anion will again accept a proton and then it is going to get converted into trans 2-butane, right? So this is going to be hydrogen, hydrogen and then CH3. So it is forming a trans compound. So this is the overall reaction with mechanism. So here what we have to remember is that non-terminal alkynes are reduced by sodium in liquid ammonia to trans-alkene. They are reduced to trans-alkene. Okay. So now the third application of Birch reduction reaction is that reduction of benzene rings. So benzene ring can also be reduced using Birch reduction reaction. That is the speciality of this reagent. We all know that benzene ring is highly aromatic, right? Even then that benzene ring can be reduced using Birch reduction reagent. So what happens here is that when you add sodium metal dissolved in liquid ammonia, okay, so there is going to be, so benzene ring, you know that it will undergo conjugation. So what will happen here is that this double bond that is present over here will be shifted to this carbon, okay, between these two carbon, and this double bond is shifted over here. So your product is going to look like this. So there is a double bond over here and a double bond over here. So here there is going to be a positive charge and here there is going to be a negative charge. So in the next step the same process. So what will happen? Ethanol is going to provide H plus. So that H plus is going to be accepted by this negative charge and this is going to get converted into hydrogen. So here there are two hydrogens added. One hydrogen is added, already one hydrogen was present. Okay. Again this positive charge is now going to get converted into anion. So 2 sodium metal are going to donate 2 electrons, right? Plus 2 Na plus. So these 2 electrons, it will occur in 2 steps. Okay, so what will happen? The benzene ring is now going to get converted into here negative charge and here 2 hydrogens. Again, this negative charge will again accept one proton and get converted into cyclohexadiene. So this is the product. So even benzene rings can be reduced using this reagent. Now the next application of Birch reduction is the presence of some groups on benzene ring. Okay, whenever we have electron donating group or electron withdrawing group attached to benzene ring, how will the reduction reaction occur? That is what we are going to see. Say for example, if I have benzene ring that contains OMe, methoxy group. Okay, there is a methoxy group on benzene ring. Now what will happen here? Here methoxy group is an electron donating group, right? Methoxy group is an electron donating group. So how will the electrons be shifting? So here what will happen is that this electron is going to be shifted like this, and this bond is going to be shifted over here. So in the next step, when you are adding sodium metal dissolved in liquid ammonia, okay, so you have OMe and this double bond is as such, and here you are having a negative charge, and then here you have another double bond, and here you are having a positive charge. This is how the electrons will shift whenever you have an electron donating group. See, basically electron donating group will stabilize the anion at ortho and meta position. Okay, so the anion will be formed at ortho and meta position. That is why the electrons are shifting like this. The negative charge will come in the ortho position. This negative charge will be neutralized by ethanol, right? The proton will neutralize the negative charge, and the negative charge is also formed in the meta position because electron donating group can stabilize the negative charge in ortho and meta position. So here there are 2 hydrogens attached. Now in this positive charge that is present over here, what will happen? 2 electrons from 2 Na plus will go and get attached over here. Thereby this positive charge will get neutralized, and this is going to get converted into, so here you are having double bond, and then here you have OMe, and then a negative charge over here is neutralized. So this negative charge is neutralized. Here you are now getting a negative charge. Okay. Again in the next step, ethanol is going to provide H plus, and this is going to neutralize this. So the final product of this reaction is we have a ring with 2 double bonds and then 1 OMe. If you look closely into the position of the 2 double bonds, so out of the 3 double bonds that were present initially, 1 double bond has been reduced, and now we are left with only 2 double bonds. Now what is the position of those 2 double bonds? The 2 double bonds are present parallel to each other. That is the first point. The 2 double bonds are present parallel to each other. Always in Birch reduction you have to remember this point. Whenever we have 3 double bonds, even in benzene ring you would have seen, the 3 double bonds have been reduced to 2. But those 2 double bonds are parallel to each other, right? So always in Birch reduction, whenever benzene ring is getting reduced, the double bonds will be parallel to each other. And the one more trick that you have to remember here is that whenever we have an electron donating group, okay, whenever we have an electron donating group, will have one double bond attached with it. Now the meaning is that there were 3 double bonds, right? Now we are left with only 2 double bonds. Out of the 2 double bonds, the carbon which contains the electron donating group, here the carbon which contains the electron donating group is this carbon. Now this carbon that contains the electron donating group will always have one double bond attached with it, okay, either on this side or on that side, and the other double bond is going to be parallel to it. So this is the concept. Now when we consider electron withdrawing group, if the electron withdrawing groups are attached to the benzene ring, how the subproduct is going to be? So if I have an electron withdrawing group attached, okay, so that is the fourth concept. When I have a substrate like this, benzene ring attached with COOH, we know that COOH is an electron withdrawing group, right? Here if I am adding sodium metal dissolved in liquid ammonia, now what will happen? We know that electron withdrawing group can stabilize the negative charge. So this double bond that is present over here is going to shift over here, and then this double bond will shift over here. So the first step, the substrate is going to get converted to something like this. So here we have one COOH. So the negative charge is present on this carbon. Okay. And then one double bond has shifted over here. The another double bond is present as it. So here there is going to be a positive charge. Now why have we shifted like this? Because the negative charge, this electron withdrawing group, will stabilize the anion. So the anion will be shifted to that position. Stabilize the anion at ipso and para position. We call it as ipso and para position. Now what do we mean by ipso position? Ipso position is the position where the electron withdrawing group is attached. Now this carbon is called as the ipso carbon. Ipso meaning on the same. Okay, in the same carbon, electron withdrawing group is also attached and the negative charge is also present. Now you have to understand the difference between electron donating group and electron withdrawing group. Whenever you have an electron donating group, the anion will be stabilized at ortho and meta position. That is why we brought in an anion first at the ortho position. First the anion was brought at the ortho position and then the anion was brought at the meta position, because those are the stabilizing positions. In case of an electron withdrawing group, the negative charge will be stabilized at, one is the ipso position, that is the carbon which contains the electron withdrawing group. Another one is the para position. That is why the shift happens like this. Okay, so the next few steps are almost similar. So what will happen here is that I'll write it in a single step. Okay, so in the first step we add ethanol. When you are adding ethanol, this part, this negative charge is going to get converted. It is going to get neutralized by this H plus. So we are going to get the benzene ring, the ring, and here you are having COOH, and then here you are having a positive charge. In the next step, when you are adding two sodium metal, okay, those two sodium metals are going to provide two electrons. So this part, this para position is now going to get one anion. Here you are going to get one anion, and in the last step again ethanol is going to donate one proton and that part is going to get neutralized. So our final product will look something like this. This is our final product. Now here also, if you check, out of the 3 double bonds we are now left with only 2 double bonds. Okay, 2 double bonds parallel to each other. And one more thing, if you check, the double bonds are not present on the carbon which contains electron withdrawing group. The double bond should not be present on carbon containing the electron withdrawing group. So if you compare and contrast between these two, between the electron donating group and electron withdrawing group, in case of electron donating group, the double bond should be present on the electron donating group. One double bond should be present on electron donating group, the other double bond will be present opposite to it, right? In case of electron withdrawing group, the double bond should not be present on the carbon which contains the electron withdrawing group. So this is something like a simple method to identify the product. Okay. Now this is the 4th application of Birch reduction reaction. Now let us look into the 5th application of Birch reduction reaction. Okay. The 5th application is reduction of alpha beta unsaturated compounds. Now, Birch reduction reaction can also be used for reduction of alpha beta unsaturated compounds. So here, if I take a substrate like this, okay, if I have a double bond over here and then a double bond here, so this is an alpha beta unsaturated ketone, right? So if I am adding sodium metal dissolved in liquid ammonia, now what will happen here? We know that this oxygen is more electronegative than carbon, right? So this double bond is going to shift over here and this part is going to get conjugated like this. So after conjugation, your product is going to look something like this. So here there is going to be O minus. So there is a double bond over here and then there is a positive charge over here. So in this positive charge, what will happen? Sodium metal is going to provide its electron. Na plus electron. So this electron will get attached to this positive charge, and in the first step it will form one radical. Okay, in the first step it is going to form one radical, and in the next step again, if sodium is providing another one electron, it is going to form one anion. Okay, so here we have O minus, and then here a double bond, and here one anion. In the next step it's obvious. So okay, ethanol is going to provide H plus, and that H plus will get attached over here. So in the next step we are having O minus, and then a double bond over here, and then one hydrogen has been attached over here. So in the last step, again this oxygen negative charge is going to shift like this, and this double bond is going to shift over here. So the product is going to be double bond O and then a negative charge. Again in this negative charge, what will happen? Again ethanol is going to provide H plus, and this is going to get reduced. So if you see overall, what has happened is that alpha beta unsaturated double bond has been reduced. That is the overall reaction that has occurred. Okay. So the reagent sodium in liquid ammonia can also be used to reduce the alpha beta unsaturated double bonds. That is the fifth application of Birch reduction reaction. Now one thing that you have to remember over here is that whenever you take an alpha beta unsaturated double bond, here we have a single ring. If we have a decalin system, okay, wherein you have two double bonds, and then if the reduction is going to occur at the junction, then always the sodium metal dissolved in liquid ammonia will always result in, after reduction, it will always form thermodynamically stable product. Thermodynamically stable product. Now if we consider decalin system, trans decalin is thermodynamically stable than cis decalin, right? So when you have sodium in liquid ammonia added to a decalin system, always trans decalin is formed. So let us understand that with an example. Okay. So here let us take this example. Okay, so we have a double bond over here, and then so this is an alpha beta unsaturated compound. So here you have, obviously you have one hydrogen. Okay, so let us consider the hydrogen is present in the wedge position. Now when I am adding sodium metal dissolved in liquid ammonia, just now we saw that this double bond that is present over here is going to get reduced, right? And there is going to be a hydrogen added over these two carbons. Now the hydrogen that is going to be added to the junction, so this is a decalin system, so the hydrogen that will be added is going to be added as trans decalin. So if this hydrogen is present on the wedge position, the hydrogen that is added over here will come in the dash position, and there is going to be a double bond O. So trans decalin is going to be formed. On the other hand, if the same reduction reaction is carried out with palladium carbon, okay, palladium carbon, what will happen is that again the double bond will be reduced. But in that case, if you have a double bond O and this hydrogen is present in wedge position, this hydrogen will also be coming in the wedge position, which means cis is formed as the major product. When you add sodium in liquid ammonia, trans is going to be the major product because it is thermodynamically stable, right? Okay, now these are the applications of sodium in liquid ammonia. Now let us see one or two questions, and then I'll end this video. Okay, so the first question that we are going to see is, so let us take the first question. We have one OMe methoxy group and one COOH group attached. Okay, so here what we are doing is that we are adding sodium metal in liquid ammonia in the first step. Then followed by the second step, we are adding C7H15Br. Okay, now we have to tell the product. Now what will happen here? See, here we have OMe and COOH. Now we know that OMe is an electron donating group, while COOH is an electron withdrawing group. Just now we saw that whenever we have an electron donating group, the benzene ring contains 3 double bonds. Out of the 3 double bonds, only 2 double bonds are going to be present in the final product. Now how should the 2 double bonds be? They should be parallel to each other. One, if you have an electron donating group, one double bond should be present on the electron donating group. Now that double bond can either be present in this side or the double bond can be present in this side. Now we know that there should not be any double bond on electron withdrawing group, right? So I'll obviously put one double bond like this in this position. Okay, one double bond over here and the another double bond will come over here. So they will be parallel to each other and they will not be present on this carbon. Okay, so this carbon will obviously get a negative charge, right? Because how will we shift the electron? We will shift the electrons like this. So this double bond is going to shift like this and this double bond is going to get shifted like this. So here there is a negative charge. So this is the product of your first step. We have performed Birch reduction and there is a negative charge on this electron withdrawing carbon. Now in the next step we are having a C7H15Br. Now Br is a very good leaving group. So the negative charge will attack this carbon and this bromine will be cleaved. So your product is going to be OMe and then there are two double bonds on parallel carbons and COOH on this carbon, and on the same carbon we are going to have one C7H15. The negative charge is present over here because electron withdrawing group will stabilize the carbanion at ipso carbon. Okay, so that is why. So this is the product of this reaction. Now let us consider a last example for this Birch reduction reaction. Okay, so the last example is the system that is given to us is we have again a two 6-membered ring attached, and then we have a double bond O over here, and then we have one CH3. Here we have one CH3 and then a double bond. Okay, we are adding lithium NH3 twice and then ETI in the next step. So sometimes Birch reduction reagent will be written like this. Basically it means that lithium in liquid ammonia. Okay, any alkali metal can be used for Birch reduction reaction. Okay, so what will happen in the first step? As you can see here, you can find an alpha beta unsaturated alkene, right? So the double bond will shift. So this double bond is going to shift over here and this is going to shift like this. So in the first step we are going to have O minus, right, and then the double bond over here, and here we are having one CH3 and then this is going to be present, and there is a positive charge on this carbon, and this positive charge is going to get converted. In the first step it will be converted into a radical, and then in the next step it's going to get converted into an anion, right? So I'll directly put it as 2 sodium and convert it into an anion because just now we saw how it happens. So here we have one CH3, here we have one double bond and then O minus and then a CH3 over here. Fine. Now if we have to understand, in the next step hydrogen is going to get attached over here and we know that it's going to get attached trans. So in the next step when we add ethanol, this this minus charge is going to get converted, it's going to get neutralized, right? So the product will be, so here at the junction the trans position is going to be, trans decalin system is going to be formed because it is thermodynamically more stable. So here this hydrogen will be attached in trans position. Now in the next step we have to add ethyl iodide. Okay, so I'll write the substrate like this. Okay, the substrate that is formed, let me write it in chair conformation to understand. Okay, so here we have one CH3 and here we are having hydrogen. Okay, and there is a double bond over here and here we have one O minus. Now what will happen in the next step? In the next step this O minus is going to get shifted over here. I'm sorry, this double bond is over here. So in the next step what will happen is that this double bond is going to shift. So this double bond will be shifted over here and this double bond is going to shift it to this carbon as negative charge, right? So here we have one CH3 on the carbon and then one hydrogen at the bottom, and here we already have one CH3 attached and then we are having one negative charge here and then this is double bond O. Now what we are adding in the second step is we are adding ethyl iodide. So this negative charge will attack this ethyl group and iodine is going to get eliminated. Now the question is in what configuration will this ethyl come, whether it will come from the top or whether it will come from the bottom. If you check the substrate that we have CH3 present on the top position, right? CH3 is a bulky group, so obviously the ethyl group is going to attack from the bottom. So the final product is going to be, we have one CH3 on the top and then one hydrogen at the bottom, and here we have a double bond O, and this negative charge is going to attack the ethyl group, and the ethyl group is going to get attached from the bottom, because methyl group is a bulky group, it is present on the top position, right? And this CH3 will automatically go to the wedge position. So this is our final product. I hope you found this video helpful. Thank you.